characterize the universality of a given critical state. Okay, so however, the long distance correlation, which means the power law decaying correlation in critical states, and the sub-extensive entanglement structure, which is a logarithmic entanglement entropy, are generally sensitive to perturbations. For example, let us assume we have some unitary perturbations. Generally, they will introduce gap in the system, right? So the ground state will no longer have these long distance correlations, and the entanglement will will exhibit area law scaling. And today, what we are interested in is how this critical behavior will be modified by weak measurement. So the basic question is that instead of a collapse of wave function to some trivial product state, would there will be some interesting features? And this leads to the concept, the so-called measurement alternate criticality. So so basically we have a given critical state, and we perform some weak measurement onto it. So this is how physically we can get some information of the critical ground state, and certainly you will find that in general, this weak measurement will break any critical behavior of the given critical ground state. But fortunately, at some measurement particle, you can still have the typical signature of the criticality. So basically, you can have power law decaying correlation function and also the logarithmic entanglement entropy, as I have introduced. These behaviors actually distinguished the general state from critical state. But let us see how this weak measurement works. And let's begin with a simple example of a quantum Ising chain. So suppose we have a initial state which is prepared as the ground state of the critical Ising Hamiltonian. So then we apply the weak measurement, basically is some generalized measurement, and the measurement strength is controlled by this parameter lambda here along x direction. So we will have the post-measurement states in terms of this. So, and the key point is that by setting a uniform measurement outcome, so basically we project each spin to the polarized direction of x. For example, let's say the state is projected to all be positive or all be negative. Well, sorry. And this particle actually can be written as an imaginary time evolution driven by the poly X operator. So to say this, you just need to do the Taylor expansion of the exponential operator, and this on-site time evolution actually this on-site time evolution are independent for each site. So basically, you can do this. Okay, so what has been found is that for this simple setup, the post measurement critical state, let's say, is critical state. Okay. So this post measurement state actually can be described by this passive integral.
Question.
Okay.
So suppose the measurement outcome is not all plus or minus, but some plus minus combination, plus minus minus. Then how does the story change?
Okay, so basically you won't have post-Merriman states that host logarithmic entanglement entropy and power law correlation. So you have to do the post-selection to get this uniform Merriman outcome to have the interesting behavior that I will introduce below.
Yeah, but suppose I do post the selection, but I select some other outcome states where the measured outcomes are not all plus or all minus, but some plus, some minus. Do I still have power law correlation and logarithmic entanglement entropy?
I think there won't be power law correlation and logarithmic entanglement entropy. So let me see. So for example, I have other types of measurement outcome. So basically, I will have some plus minus and site-dependent plus minus in the imaginary time evolution operator here, right? So in this case, as I will introduce to you soon, so basically this defect cannot be written to be some defect conformal field theory. So I will expect the two-point correlation function will no longer be power law, and the entanglement entropy also will be no longer logarithmic.
I see. Thank you.
Okay. So in this case, where I have a uniform measurement outcome, I can write down this time imaginary time evolution just simply as a defect located at tau equals to 0 with, in the past integral representation here. So here in the Ising CFD, we have the sigma x operator is or at the leading order of the sigma x operator is actually a primary field with dimension 1/2 in the Ising CFT. So I can consider this imaginary time evolution as a defect line. This defect line is not as usual along the position equals to 0. It's along the time tau equals to 0. So basically, I have the action like this. I have the action consistent with first the original Ising CFT action, and then the defect action, which is just a defect line here. So the space-time rotated version, which is a defect line located, for example, in x equals to 0. This series actually solved a long time ago by Oshikawa and Affleck. And this information are actually very important for determining the correlation function and entanglement entropy. Later, I will show that. Okay. So suppose we want to calculate the half-cut entanglement entropy. We will introduce a branch cut here. Oh, sorry. So basically, suppose we have a subsystem A that is from minus infinity to x equal to 0. So I introduce a bar chart for cutting this subsystem. And this configuration can be conformally mapped to a cylinder with two defect lines. The first defect line located at the imaginary the imaginary direction have a value of 0 and theta equals to pi, these two position. Okay, so to see this is actually related to the space-time rotated version of the path integral. Let us consider the following. So to calculate the entanglement entropy, so this is actually the the passive integral representation of our reduced density matrix. So in order to calculate the entanglement entropy, we need to take logarithmic of this passive integral. But this is actually very hard to do in the field theory. So basically, we need to introduce a replica trick here. And this translates the calculation to the unshaded partition function, okay, which is linear in the reduced density matrix here. So in this language, I will need to introduce n copy of the defect, the Ising CFT. Okay, and after conformal mapping, I can still map this configuration to a cylinder, but I will have two n defect line now. Okay, so if I take trace, this is just a cylinder with two n defect line and without the bunch cut here. Okay, so is that clear? Okay. So suppose now we consider the defect line is along x to 0, and we still want to calculate the half-cut entanglement entropy. And by conformal mapping to a cylinder, we still have a cylinder with a branch cut that introduced by the entanglement cut and two defect line. If I take the trace, so the branch cut will be invisible. So this configuration will be just the same as this configuration. So basically, what does this mean? This means that in sense of computing half-cut entanglement entropy, these two series are actually equivalent. So based on this, we can reach the analytical solution of the entanglement entropy because this the right part, the defect line is along a given spatial position is actually already being solved. So basically, it's just Ising transfer field Ising chain with deformation of the bound strengths in the middle of the chain. Okay. This actually also works for the general configuration. So what we have told is that we want to calculate the half-cut entanglement entropy, right? So this actually can be generalized to general configuration. So suppose I still have this passive integral of the defect series, and I introduce a subsystem A here, and still, this configuration can be conformally mapped to a cylinder with two defect line, which is solvable as we have introduced. Okay, so and these are completely analytical calculation, and we can also do numerics of this post-measurement state. And what people found is that, okay, so as an analytical solution suggested, we have a parallel decaying correlation after measurement, and we also have a logarithmic entanglement entropy after measurement. And it actually gives a continuously varied effective central charge in the scaling behavior of the entanglement entropy. And this relation with the measurement strength is actually identical to the defected ground state. Okay, so this is what we know from the existing literature. Any questions? Okay, so what we are interested in now in this work is the entanglement Hamiltonian. So entanglement Hamiltonian in two-dimensional safety is actually calculatable if we are focused on the case of cutting a single interval from the ground state. So again, we do a conformal mapping to a cylinder. And let's say here we're starting from a field theory without defect. It's just a critical ground state. Okay. So by doing this conformal mapping to a cylinder, we have the entanglement Hamiltonian on this cylinder is actually the same as a physical safety Hamiltonian. To see this, you just need to consider the cylinder is path integral representation is just a thermal state, right? So the Hamiltonian there is just a physical Hamiltonian because it's thermal state. Your reduced density matrix is just E minus beta H. Okay. So this actually lead to analytical solution of the entanglement Hamiltonian for general safety ground state. It's just fully determined by the energy momentum tensor of the original critical CFT Hamiltonian, and the mapping to the cylinder is purely local. And as we know, the safety Hamiltonian are always gapless. So this entanglement Hamiltonian here is actually also gapless. So yeah, this is what we, okay.
Yeah. After dividing the F Z prime, how do I know this Hamiltonian is necessarily gapless?
Okay, so it's not so obvious from this expression, but if, there are two ways. So suppose we are interested in calculating the trace of the rho A or trace of rho AN. So we have two methods to calculate it. We can define a Hamiltonian in this direction and involved around the imaginary direction, right? And another method is that we consider the Hamiltonian here and evolve in this direction. And these two should give the same result. And by doing some calculation, you will find this equivalence will give you the result that the entanglement Hamiltonian should be proportional to the CFT Hamiltonian.
Okay.
Yeah.
Thanks.
Okay. So now
Sorry,
okay.
a question. A related question. So by saying CFT Hamiltonian, you meant that the Hamiltonian for the field theory or the Hamiltonian for the originalizing model?
For the field theory.
I see. And another question is, how did you map the left diagram to the right one? I cannot see it.
Okay. So basically, here this circle, for example, is mapped to the left circle of the cylinder, and here the right circle is mapped to this right circle of the cylinder.
Then
and
what about the boundary, the outer boundary of the left diagram?
Oh, here the total system size is assumed to be infinity. Okay.
Okay, I see.
Yeah.
Thanks.
Any other questions? Okay. Okay, now let us consider the case with defect line. We can still do the same conformal mapping to a cylinder, but now on the cylinder we'll have two defect line, one located at theta equals to pi and one located at theta equals to 0. For this case, the entanglement Hamiltonian is actually some kind of average of the physical Hamiltonian and the two defect line here. Unfortunately, we do not know how to solve this case from the CFD context. The solution is still unknown. So generally, by doing this mapping, we cannot tell anything about the entanglement Hamiltonian of a critical state after doing this weak measurement. So that's a technical issue. And here, to get some understanding of the entanglement Hamiltonian after the weak measurement. We consider a simple case. We do not consider general CFTs. We consider critical Dirac fermion. So what's nice in the case of Dirac fermion is that the Gaussianity of free fermion actually allows us to calculate the entanglement entropy, to calculate the entanglement Hamiltonian just from the 2-point correlations. Okay. So basically, we're starting from the lattice model. We have a tight bounding model and prepare the ground state at half filling as a starting point. And we perform a weak measurement, and the weak measurement is driven by on-site potential even odd. This style is just a master of the free fermion. And after applying this type of weak measurement, we can calculate the 2-point correlation function. We will say what we say that the 2-point function is still polar decaying. It's still 1 over the distance. It's just the per factor and the on-site terms are modified. So basically for the critical ground state, we will have these on-site terms are always be 1/2, do not have any even odd effect. And here we will not have this per factor. Okay, that's a critical ground state case. Now, after the performing the weak measurement, the modification is very slightly, just on-site terms and the per factor of the polar decaying term. Okay. We can, okay, so to solve the entanglement Hamiltonian, we consider the continual field theory description of the lattice model. So basically, we have a Dirac fermion that is driven by the imaginary time evolution, which gives this equation of motion. And the initial condition is a ground state solution of the Dirac fermion. Okay, so we can get the consistent result of the 2-point correlation function. It has this very nice structure, which allows us to solve it analytically. Okay. So to do the calculation, the first step is to, okay, so the logic is this. We have the 2-point correlator, and to calculate the entanglement Hamiltonian, we will need to take a logarithm to this and inverse to the 2-point correlator. And to do that, we need the spectral information, which means that we need to diagonalize this 2-point correlator. Okay, so to do that, recall we actually know how to solve the single interval entanglement Hamiltonian from the conformal field theory. It's, as we have introduced, is just by considering conformal mapping to the cylinder, where the entanglement Hamiltonian is actually identical to the CFT Hamiltonian. Okay. So the key point here is that this actually means that we can use the same eigenfunction to diagonalize the entanglement Hamiltonian. So in this case, we have the CFT Hamiltonian is just the free massless Dirac fermion Hamiltonian. It can be diagonalized by the plane wave on this cylinder. Okay, so this means that the entanglement Hamiltonian can also be diagonalized by just the plane wave on this cylinder. Okay. So basically, we can write down the entanglement Hamiltonian in terms of this integral. So basically, phi here is just the plane wave on this cylinder with some normalization factor. Okay, and the zx here is just from the infinite plane to the cylinder, the conformal mapping. Yeah. we can do some check about the solution. We just need to integrate it back, and after some straightforward algebra, we can actually say that the entanglement Hamiltonian is the same as a CFT solution. Okay, so this is our starting point. The entanglement Hamiltonian can be diagonalized by the plane wave on the cylinder. Okay. So now let's go back to the free fermion case where the entanglement Hamiltonian can be calculated by just the 2-point correlator. So what does this mean? This means that the 2-point correlator can also be diagonalized by the plane wave on the cylinder. So again, just after some straightforward calculation, we can have this 1/x minus y operator can be diagonalized by the plane wave on the cylinder, okay, with eigenvalue like this. Is there any questions so far? Okay. So now we have the spectrum decomposition of this 1/x minus y operator. And we have the 2-point correlation function just contains two operators. First is a delta function, and second is this 1/x minus 1 operator. So we can solve the spectrum of the 2-point correlator after weak measurement. So basically, we will get the eigenvalue like this, and the eigenvector like this. An important thing here is that the eigenvector of the entanglement Hamiltonian, which is phi sx introduced here, is actually just a unitary transformation of the case of ground state. So basically, it's just a unitary transformation. Okay. And from this spectrum decomposition, we can actually have many interesting conclusions. So the first thing is that we have the mapping between the entanglement spectrum before and after weak measurement, which is just from the eigenvector eigenvalue of the 2-point correlator. Okay, so this gives that the S pi S here is 2 pi S is a entanglement spectrum after weak measurement, and 2 pi S0 is an entanglement spectrum before weak measurement. They are connected by this formula. And the consequences of this mapping is that it shows there is always a finite gap after weak measurement, and the gap is proportional to the strength of the weak measurement beta here. Okay, so we actually also do the numerics on this free fermion lattice model, and we found that this mapping works very well, just like the figure shown here. Okay. And another point here is that this relation, I mean, this mapping between entanglement spectrum before and after weak measurement is actually identical to the mapping of the entanglement entropy before, with and without a conformal defect that introduced in the middle of the overall free fermionic chain. Okay, so this is again consistent with the space-time rotation picture that we have introduced in the beginning here. Sorry, here, this mapping. Okay. Is there any questions so far? Okay. And also, from this spectral decomposition, we can analytically calculate the entanglement entropy. So An interesting thing here is that the entanglement entropy is actually follows this separation. So the entanglement entropy can be written as two parts. The first part is an integral over the product of the eigenvector of the entanglement Hamiltonian. And this integral actually controls the scaling behavior of the entanglement entropy. As long as the product of the eigenvector of the entanglement Hamiltonian is unchanged, we will always have the same scaling behavior, no matter what operation we all apply on this critical ground state. Okay, and another part of the is also an integral that it controls the effective central charge that are shown as a perfactor of the logarithmic scaling of the entanglement entropy. Okay, again, we can get the same result just as a free fermion chain with a conformal defect. Okay. Is there any question? Okay. And again, we can do the numerics on lattice model, and all works well because we are dealing with some free theory, which, as I introduced, all things are analytically calculatable. Okay. So now we are going to the main result of our work. We can calculate the entanglement Hamiltonian of the post-Merriman state, and this is what previously has not been done. Actually, actually we cannot get a closed form of the entanglement Hamiltonian due to mathematical difficulty. And if you look at this formula, we will have the kernel of the entanglement Hamiltonian is given by this integral. And this integral is so complicated. So instead of explicit computation, we consider an effective theory by performing the Taylor expansion around S0 equals to 0, which is recall that S0 is a entanglement spectrum of the critical ground state. Okay, so basically it's just a low energy expansion. And we can have the diagonal term of the spinor. So recall that we are dealing with a Dirac fermion. So all entanglement Hamiltonian will be in a spinor form. And the diagonal term of the spinor will give you some only odd terms, odd power of the S0. And off-diagonal term will give you even terms. And if you consider an integral, so we are doing some legal things here. We exchange the integral and the summation. And if you do this exchange, you will find that the Fourier transformation of the power function of S0 actually will give you some infinity many higher order derivatives of the field operator in your entanglement Hamiltonian. And this actually, after doing the discretization on lattice, you'll find that they are possibly to give you long distance terms on lattice model. Okay. So this is
here when n is can you translate this expression to, if I do a discretization on lattice, can you translate this result to how fast the interaction decays?
In principle, we can get to that, but since the coefficient D and H here are actually very complicated. We do not have the general form in terms of N, so we do not do this calculation.
Mhm.
Mhm.
In principle, this non-linear interaction may be actually irrelevant, right?
Yeah, that's also true.
Yeah, so in that case, the non-local nature of this interaction is not very important.
Yeah, right. But later we will show that we do the lattice calculation, and on lattice we do actually say that it's long-ranged.
But the question is whether it's relevant or irrelevant compared to the short-ranged part of the theory.
Yeah, for this thing, we cannot say from this naive calculation here. Yeah. Mhm. So basically, the thing that the integral representation of the entanglement Hamiltonian is so complicated, so we do not have a closed form. And the only thing we can do here is to do some expansion and try to figure out, is there anything that could be universal and also can be observed in the lattice calculation. Okay. So is there any question more? Okay. So if I just look at the lowest order where n equals to 0, we will have the entanglement Hamiltonian actually from these two parts. The first part is diagonal part, and the second part is off-diagonal part. The diagonal part is actually just a slightly it's just slightly different from the critical ground state. So it has the same structure, which is a T00x over Zx derivative here. And this perfector here is a monotonic decreasing function of the measurement strings beta. And what interested is the second term. The second term is off-diagonal term that couples chiral and anti-chiral parts of the entanglement Hamiltonian. So basically, this is a math-like term, but later I will show that this is actually something not so perfectly matched with the lattice result. But it actually indicates there could be a linear gap of the entanglement Hamiltonian, just as we discussed before from the exact mapping before and after Rick measurement. So to test this naive solution, we can take the limit beta to 0 and it will reproduce the well-known ground state result. Okay. And if we rarely do the numerical calculation on lattice model, so what we will find that, yeah, we actually have an on-site term that exhibit an even odd effect, just like the mass term of the free fermion. But what the analytical calculation cannot explain here is that there is a position dependence of the on-site terms. But in the calculation here, I mean the naive calculation after we doing the dangerous exchange of the integral and the summation and keep opening to the lowest order of n, we got this mass-like term that does not depend on the position. But on the lattice, we found it actually depends on the position, and this position dependence is something we cannot explain naively from the calculation here, but it could be recovered if we consider the calculation to infinity many order of n. Okay, so it works well for the nearest neighboring term, which is given by this part. So basically, this first order derivative of the field operator on the lattice, it will become the nearest neighboring hoppings. So although I do not present any scaling fitting here, but actually these curves are fit well with this function 1 over z prime x. Okay. And the perfector of these nearest neighboring hopping terms actually also monotonically decreasing with increase the measurement strength beta. Okay. And if we consider higher distant hopping terms, numerically we found that the higher distance hopping terms, the strength of these hoppings actually scales in a polynomially way with the distance between two sides. And the exponent of these parallel decays actually quite seems very stable. The even terms will give you an exponent near 2, and the odd terms will give you an exponent near 1. But although these results are very nice on lattice models, but we cannot obtain this from the analytical calculation from the field theory. Okay. Is there any question? Okay, let's move on. Okay. We have talking about the single interval entanglement entropy and entanglement Hamiltonian. And what interested in the free Dirac fermion thing is that it allows us to extend the calculation to multi-interval cases. So basically, the idea is actually very simple. So suppose we have, we have already introduced that the entanglement Hamiltonian and the entanglement entropy can be solved, of the single interval can be solved by introducing a mapping from, for example, cutting a subsystem from an infinity plane to a cylinder. And now here we will consider mapping multiple intervals again to a cylinder. So this generalized mapping will be in this form. Okay, but the problem is that this mapping is generally not conformal. For example, if we consider the two interval cases as an example, we will see that there are some singularity at these points where you will find that the derivative of this mapping equals to 0, which means that it's not a conform mapping. So in general, we cannot extend the calculation to multiple intervals. Okay. But what's nice here for the free Dirac fermion is that the mapping actually works. Okay. This can be shown by just considering a purely algebra calculation of this spectrum decomposition. You will find the eigenvector is solvable in this case. It's again basically just the plane wave after a mapping to the cylinder. It's just now the mapping is not actually conformal. Okay. And the mathematics here is actually also very interesting. So basically, this mapping works because there is an isomorphism between a single free fermion field on multiple intervals to multiple free fermion fields on a single interval. So this is a basic reason why we can do this calculation, and it does not apply to any other general CFT. Okay. And this allows us again to calculate the entanglement spectrum analytically and the entanglement entropy. So first, we look at the entanglement spectrum. Again, we have the same mapping before and after Wick measurements is unchanged. And it also indicates a finite gap that linearly in the measurement strings as shown here. Okay. So again, we can also calculate the entanglement entropy in a very similar way. And this integral over the entanglement spectrum S will give you again just the perfactor of the logarithmic entanglement entropy. And if we look at the product of the eigenfunction of the entanglement Hamiltonian, that as I have introduced, it controls the scaling behavior of entanglement entropy. You will find that it's in this simple form, and it is only determined by the mapping to the cylinder. Okay. For example, let's look at the two interval case. This calculation will lead us to this very nice form of the entanglement entropy. It's identical to the ground state, the scaling behavior. Just as the central charge is changed to an effective one. Okay, so we can also test this on our lattice calculation, and it again works very well. Oh, so that's a basic story of today's talk. So basically, what we have done is that we calculate the entanglement Hamiltonian of the free fermion after Wick measurement. And this is based on the fact that all information of free fermion are encoded in just 2-point correlators, which is modified slightly by the Wick measurement. And since this 1 over x minus y operator is solvable, we can derive the analytical expansion of both entanglement Hamiltonian and of both entanglement entropy and entanglement Hamiltonian. Okay, so for the entanglement entropy, we found that the critical scaling behavior is actually only controlled by the eigenfunction. Actually, is a product of the eigenfunction of 2-point correlator, which is unchanged by the Wick measurements. This holds not only for the single interval, but also for multi-interval cases. Okay.
So this point is only for free fermion. The second point also only applicable to free fermion?
Actually, no. If we look at the Ising CFT, let's go back to the let's see here. So basically, you will find that the 2-point correlation function of x is also unchanged. I mean, the exponent here is unchanged by the Wick measurement. And this will control the scaling behavior of the entanglement entropy. Yeah. So I believe this is some property that general to the critical ground state after this kind of Wick measurement. And we are still working on this part, but we think this is some general property of general CFTs. Yeah.
But The Ising CFT can also be viewed as a free fermion, but coupled to some Z2 gauge field. Maybe the
Yeah,
Z2
yeah,
gauge
that's
is
true.
not important here,
Oh,
and then it just becomes free fermion.
yeah. Yeah, I agree. The icing safety example is too naive here. Yeah. But this can also be actually this kind of behavior can be also be observed in the Latinger liquid. So if you apply certain mass like imaginary time evolution or say let's say weak measurement to the ground state of a Latinger liquid, you will again get the logarithmic in time entropy. And again, the polar decaying to point correlator with unchanged exponent.
I see.
Yeah, so yeah, I think this can be somehow proven for general safety, but is I'm still working on this. It's not fully accomplished. Yeah.
So just to make sure, previously you mentioned some analysis can only be carried out for free fermions. That analysis is not for the entanglement entropy, but for the entanglement Hamiltonian.
Oh, okay. So this is only for the single interval entanglement Hamiltonian and only for multi-interval entanglement entropy. So basically, we do not know how to calculate the entanglement entropy for multiple intervals for general CFTs.
So do you mean you do not know how to calculate the entanglement Hamiltonian for multiple intervals for general CFT?
There are two things. So first, we do not know how to calculate the single interval or any multiple interval entanglement Hamiltonian for general CFT. So basically, for the calculation of entanglement Hamiltonian, we only know how to do for free fermion. Okay. The second thing is that for the single interval entanglement entropy, we can calculate it for general CFTs. Yeah, but for multiple interval entanglement entropy, we only know how to calculate it for free fermion.
I see. Thank you.
And this actually, there are some interesting maths behind. So basically, why this spectrum can be solved mathematically? This is or I shouldn't say this too mathematical. So basically, well, let me. So basically, let us consider the case of only two intervals. Okay. This mapping is not conformal because at these 2 points, the angle after the mapping is not preserved. Okay, but this problem can be solved by considering an RB4 theory of the free fermion. And the important thing here is that the RB4 theory of two copy of free fermion is still conformal. In general, they are not conformal, but for free fermion, it's still conformal. So this mapping to the cylinder is actually not conformal for a single free fermion field on two interval, but is conformal for the two copy RB4 theory. So this is a reason why we can do the mapping to calculate the entanglement entropy here. Okay. And the last point of our result is that we found that the post-measurement entanglement Hamiltonian is gapped and long-ranged, although we cannot say something for sure from the analytical result, but the lattice calculation actually indicate we do have a gapped long-ranged entanglement Hamiltonian, even for the single interval case. And this is very different from the ground state case where as I have introduced, the entanglement Hamiltonian is gapless and local. Okay. And our work actually also leaves some open questions. So the first is that we have this very complicated form of the entanglement Hamiltonian, and can we get a closed form? If we can, we will able to say something certainly for the long-range nature of the entanglement Hamiltonian after weak measurement. And another thing is that is the calculation here. So the calculation here are basically based on the field theory description at continuum. Is the solution can be extended to the lattice case just from the lattice model, just as a ground case. So there are some solutions analytically we can get the entanglement Hamiltonian of the critical free fermionic ground state. Yeah. And another question is that, which I think there could be something more deeper here, is that in the calculation we found that in the logarithmic scaling behavior of the entanglement entropy is actually only determined by the product of the eigenvector of the entanglement Hamiltonian, which is actually the real space distribution of the eigenvector of the entanglement Hamiltonian. And this invariance of the critical entanglement scaling, could it be extended to general CFTs? And we are also interested in what physical process can respond to this invariance. So this is the first example. We know that there is an there is a physical process for which the eigenvector of the entanglement Hamiltonian before and after the weak measurement are owning up to a unitary transformation. And we are seeking for any other interesting physical process that also correspond to this kind of invariance. Okay, so that's today's talk. Thanks for your attention.
Thank you, Qizhen, for the very nice talk. Any other questions?
I want to ask some simple question that how do you distinguish the weak measurement and the strong measurement kind of means how do you define the weak measurement?
Oh, okay. So the definition of the weak measurement is in the measurement operator. Let's go back to the slide. So here we have a generalized measurement operator. It's not a projective measurement. It's parameter. The strength of the measurement is actually controlled by the parameter lambda here. So if we take lambda to 1, this will be a complete projective measurement. But if this lambda is a finite value between 0 and 1, it will be weak measurement.
Basically, in the standard strong measurement or projective measurement case, if we measure sigma x and we obtain the eigenvalue to be 1, we know the qubit is in the class state. But here, even if we get this measurement outcome, there's still a probability for the qubit to not be in the class state.
Yeah, right.
Okay. Thank you.
I want to ask you a question about the relation between your work and some previous work. During your talk, you cited many papers like the ones on this slide. And am I understanding correctly that in the previous papers, they thought the critical state after the measurement, at least for this particular set of measurement outcomes, the state is critical, and your work is saying actually, although some part looks critical, but some other part doesn't look critical.
So the previous literature on this topic, actually they only focus on the scaling behavior of the correlation function and the entanglement entropy. So that's the reason why they say it is critical. And the supportive thing is that this picture works. So basically, the weak measurement, the state after weak measurement can be somehow mapped to a defected CFT. Okay, that's basic things about the criticality after weak measurement. Here we show that although we have observed these two typical signatures, which are the power law decaying correlation function and the logarithmic entanglement entropy, we can still cannot say that for sure that this state is actually critical, in the sense that it does not described by any local CFT. Yeah.
Any other questions?
Actually, I want to add something for this question. So, actually, we cannot say for sure if this post measurement state is a ground state of any kind of conformal field theory, because we only rule out the possibility it is a ground state of some local conformal field theory. It is possible that it is a ground state of some kind of non-local conformal field theory, but we do not know how to prove this, or yeah.
What does non-local conformal field theory mean?
Okay, for example, I mean the Hamiltonian is not local, it's long-ranged. For example, there are some famous model long-range Ising chain. You can still have the ground state is described by some kind of conformal field theory, but the Hamiltonian is actually non-local.
But personally, I would think this non-local Hamiltonian is not that important in the sense this ultimately the ground state is described by some SNCFT at large distances. So there's
Yeah.
one non-local Hamiltonian that gives rise to this Hamiltonian, but there may also be some other local Hamiltonian that gives rise to the same ground state at large distances.
Mm-hmm. Yeah, yeah.
I think one interesting question is if I just consider a non-local Hamiltonian, even if it's gapped, the correlation function in general it has power law decay. So what's the most efficient way for us to distinguish such a state compared to a CFT ground state? One way described in your talk is to use the entanglement Hamiltonian, but as you also demonstrated, calculating the entanglement Hamiltonian is generally pretty hard. I wonder if there's any simpler way to distinguish these two types of states, for example, just by measuring some correlation functions.
I do not know, but the best case is that the space-time is not symmetric, so we can just marrying the dynamical opponent by calculating some correlation function. So if it's not equals to 1, so it won't be conformal.
Yeah, but I wonder if there's a way to distinguish these two types of states just from the wave functions of the states without looking at the dynamics.
I do not know the answer. But this is indeed a very interesting question.
Okay, any other questions? Okay, if not, let's virtually thank teacher again for the very interesting talk. Thank you.
Thank you. Thank you for the invitation.
Sure, and we can all leave, and next week at the same time we will have the other talk, the next talk. Yeah, bye.
Bye.
Recordings.